So today we're going back to our previous problem where we have a bar of some material with a constant thermal diffusivity and where we had derived a spatial discretization for our temperature profile. So something like this. So we have our T at position J, n plus 1, equal to T, J, n. So T at time equals n at position J, plus this alpha times delta T over delta X squared. This is our R value times our Tj plus 1, so position J plus 1, plus, or rather minus 2 Tj times n plus Tj minus 1 times n. So we had derived this much in our last video. But now we're going to be talking about something called the Crank-Nicolson method, which is another way for us to be able to solve differential equations that have to deal with diffusion. So something that looks like this equals alpha delta 2 and then some position here. So Crank-Nicolson is a method for us to be able to find a solution to this differential equation. And the way that works is now we're going to take an average. We're going to take an average of these few terms here for now time equals Tn plus 1. And everything else follows suit. So go here. Plus Tj minus 1 and plus 1. So now, take a step back and now we see that this Crank-Nicolson method requires us to do some implicit differencing, because the thing that we are concerned about is that temperature of everything that is in the middle. So we, in our problem statement, defined that we have a 50 degree and an 80 degree face on either side of our bar. So we had 100 discretizations, and we knew the temperature of the first and the very last. What we were interested in was how the temperature changes over time, how that temperature profile evolves over time for the middle 98 segments, which are temperatures that we don't know. However, in order to do this solving, we need to know exactly this. So we have this Tjn plus 1 term both on our right hand and left sides of our equation. So this implicit differencing is how our Crank-Nicolson method actually functions. And what we'll be doing in this video is setting up a spatial matrix for this differencing to be able to solve these simultaneously. So my first step here, I'm just going to clean this equation up a little bit. And for this Crank-Nicolson method, I'm going to change the definition for R and make this our R. So now I recognize that I have n plus 1 terms on this side, and I have an n term on this side. So I'll keep my n terms on this side, and I'll put the n plus 1 terms over to the other. So what we have on this side is we're going to have an R multiplied by this Tn plus 1 at position J plus 1. So if I put this over to the other side, I have minus R J plus 1 and, well, gotta have the temperature over here. Tj plus 1 at n plus 1. I recognize that I already have a Tjn plus 1 term here. I have a Tjn plus 1 term over here. So what I can do is it's R times this. So I have actually minus 1. No, because this is a negative over here. So I'll have a plus 1 plus 2r times t sub j super n plus 1. And then my last term here follows suit, r of t j minus 1 at n plus 1 is equal to, so now I could just multiply the r through here. So t r times t j plus 1 at time n. And now I'll have a plus 1 minus 2 r times t sub j n plus r t j minus 1 n. So this is just a little bit cleaner. Now, what we recognize for this n plus 1, so at time equals 0, so if n is equal to 0, right? We know this temperature, we know this temperature, and we know this temperature because we know our initial steady state, and we know that initially our TJ is all 20 degrees Celsius. That's what our initial temperature of our bar. So we have our temperature at position 1, our temperature at position 100, the 98 in the middle are all 20 at time equals 0. That isn't necessarily the case for this. Now, at J plus 1, we know that temperature because that's defined. At J minus 1, we know that temperature because that's defined. It's the same as this and this here, so that's kind of time constant. What we don't know are these 98 unknowns in the middle. So we have 98 equations to solve 98 unknowns, and that's the issue with this equation right now. So what will help us solve these 98 unknowns, however many unknowns, is going to be setting this up into a matrix format. So that'll be the next step in deriving this Crank-Nicolson relationship. So let's get started. So first, I'm going to set up my matrix of unknowns. So like I said, we have 98 unknowns, but we can account for all the temperatures. So I don't know why that doesn't want to straighten out, but so at the very top and the very bottom boundaries, we'll have our temperature at the right-hand side and our temperature at the left-hand side. So actually, I'll start this at the left. Let's go left to right. So temperature at the left, temperature at the right. Everything in between are things that we want to calculate. So we have our T1, T2, T3. And in our case, where we had 100 discretizations, if we already know 2 of them, what's left are 98 segments. So here is sort of an unknown matrix. 98. Now, when we set up our matrix multiplication, we're going to have, so I'll make this a bit wider. So we're going to need to have a 98 by 98 matrix and then a 98 by 1 matrix for our unknown. So we get a 1 by 98 a 98 by 1 matrix of all of our unknowns here that correspond to these unknowns rather. But see what happens here. So let's choose T2 here. In this case, if J equals 2, then J plus 1 has to equal 3. J minus 1 has to equal 1. So when we set it up for T2, our T1 is to be multiplied by minus R. So we have minus R in that column. Our T2 needs to be multiplied by 1 plus 2R. 1 plus 2R. And our T3 needs to be multiplied by minus R again. So minus R. How about if our J was equal to 3? Well, I think you can see where this is going. So our J equals 3. Our J plus 1 has to equal 4. Our J minus 1 has to equal 2. So now our T2 needs to be multiplied. Our T2 needs to be multiplied by minus R. So T2 lines up with this column. And then our T3 needs to be multiplied by 1 plus 2R. And our T4 needs to be multiplied by minus R again. So let me just draw like some grid lines here almost. We're almost kind of creating these diagonals of values. And every spot that doesn't have a value gets a big old 0. So this is 0, continuing all the way on. There'll be like a 0 here, continues all the way on. And that'll continue for this entire matrix. So if we were to go to T1, well, we can't have a T0, so our T1 has to line up with 1 plus 2R. And then we have a minus R left for this one. Then we have a 0, and then a 0, continuing all the way on. So this kind of diagonal that we're creating here. So this diagonal is being filled with 1 plus 2R. This diagonal is going to be filled with minus R. This diagonal also filled with minus R. This is kind of how you're able to set up that matrix that is representative of our Crank-Nicolson method that we have derived thus far. So that makes intuitive sense when we plug in these little markers. And this is going to help us plug these into Python and actually give us those same temperature profiles using a different method. So let's start filling out our product matrix. I still have it right there. So for our product matrix, what we're basically doing is this cross product. So let's start on this row for T2. So for T2, we have this T1 minus R. So minus R T1. Then we have 1 plus 2R. So plus 1 plus 2R times T2. And then T3 times minus R. So minus R T3. And you can repeat for the bottom one, right? So now if we do this times this, we have a T1 times 0, so we don't account for that, minus RT2, so minus RT2, plus 1 plus 2RT3, minus RT4. So basically just upping that indexing. But you might be looking at this and wondering, well, what about this one at the very top here? So let's look at this, right? If we were to multiply at the very top, our t is equal to 1. So let's go back to this case. In fact, let me just copy and paste this somewhere else so I have room to explain. So remember that we defined that we have a temperature on the left-hand side and a temperature at the right-hand side. Oh boy. So that basically acts as our T1 and our T100. So our temperatures on both sides of our, on both sides of our bar. We also recognize that always stays constant because we defined in our problem statement that that end, so at that position 1 and that position 100, those two values are constant. So that's defined in our problem statement. So let me go erase all this. So we want to know what this equation looks like when j is equal to 1. Well, unfortunately, j minus 1 is 0. J plus 1 is 2. But we also know that if we're going all the way to the left-hand side, so that position 0 per se, that's actually just our temperature of L, temperature at the very left hand, which is 50 degrees Celsius as we defined it. So let me also do the same for this side. So J plus 1, 2, J, 1, J minus 1, 0. Now, we have these two for Tn plus 1. Everything here is for time n, and technically, this is also true for time n because this temperature at position 0 is remaining constant for any time. So we can actually bring this over to this side to get this final equation. So 1 plus 2r T1 n plus 1 minus r T2 n plus 1 equals r T2 times n plus 1 plus 2r T1 times n plus 2r TL. And I'm not going to put the n superscript there because it's kind of redundant, because that temperature at the left hand side, similarly for the right hand side, is always going to be equal no matter what the time is. So now we basically have this. So if we were to multiply T1 over here, we get that. If we were to multiply T2 over here, we get that. Everything else is zeros. This is equal to this side of the equation. So I'm actually going to write this over here, and I'll follow that ascending order. So 2r TL plus 1 plus 2r times T1 at the previous time plus what's that say? R times T2. So we have actually a solution for this first matrix multiplication using our boundary conditions that we have defined early on in our problem statement. So really quickly, a conceptual thing that might have gone overlooked is that these temperatures here for temperatures at n plus 1. So these are all for Tn plus 1. These are the unknowns. And so actually you might have found that I made a little arithmetic, or I guess more of a translational error here. There should be a minus 2r. And these temperatures are all at the time previous. Well, if I want to put these in terms of the previous time, I simply just have to use the counter on my right side of the equation instead of the left side of the equation. So I'm actually going to rewrite this in terms of the right hand of my equation. So what that looks like is for our j is equal to 2, let's say. Yeah, for our j is equal to 2. So our j plus 1 is equal to 3 at the previous time. We have a 1 minus 2r at j equals 2, previous time. And we shouldn't even have that minus here. This is all pluses. So r times t3, or this should be t1 now because it's a j minus 1 time n. So let's repeat that for the rest. T4 times at t equals n minus 2r t equals, or t at time equals n at j is equal to 3 now. And now we have r times j minus 1 for position 3 is 1. Or 2. Because, yeah, 2. We have 3 minus 1 is equal to 2. So this continues on, and we'll have a familiar product for the temperature all the way at the right side. So now we have this matrix in terms of our left hand of the equation here and our right hand of the equation here. So that looks a little bit better for us to be able to manipulate. So really quickly, we can just write down what the expression for our right hand side is going to be. And it's going to kind of mimic this equation here. So we're going to have 2 times R times our temperature at the right hand side. And basically for this, our J counter is 98. So we'll have 98 here. So plus 1 minus 2R T98 at the previous time, and then our J minus 1 is going to be 97, so plus R T position 97 at N. So basically now what we have done is we've constructed our matrices in order to be able to solve this matrix, which we actually call a banded matrix. And the reason we called it a banded matrix is because we have visible bands. We have this lower band, that's our minus R, that carries on through. We have this middle band, which is our 1 plus 2R, and then a top band over here, that's minus R. So these constant values that kind of show itself throughout the matrix are what's known as banded matrices. And another thing we can define this as is something called a sparse matrix. And sparse means that we have these 2 or 3 values here, and everything else is a 0. So we're only focused at a handful of values at a time. So solving these sparse banded matrices is what's going to help us develop these temperature profiles at Tn plus 1 and so on and so forth. So let me bring over this Python notebook. So if we remember, we have an R value that we set, and we also created this this temperature matrix. So if we show it down here, let me get my keyboard out. If we show that matrix here, so T, actually I don't want to initialize it like that, so I'm just gonna copy and paste this much over here so we can do a Crank-Nicolson analysis. And I'll add that here. I'll say this is Crank-Nicolson. Right, so we've created this new section header. If we look at T, here is our initial state. We have 100 divisions. I'll redo this here. So we have 100 divisions, and we have our left-hand temperature equal to 50 degrees, our right-hand temperature equal to 80 degrees. And I'm also going to carry over this R value too. So, and you know what I'm going to do? I'm going to set this equal to a value that we know will make our situation unstable, because we know from our previous video that this 0.5 is actually the maximum value our R can be to provide a stable solution. If we provide anything else, we get really crazy things happening in our temperature profile graph. So I'll keep this back at that limit, get our nice bands as we approach our steady state. And now we'll be able to use a Crank-Nicolson analysis to maybe get a stable solution even though we have an R value that's outside of our range. So let's carry on with that. So let's begin constructing this matrix here. So we recognize that we need to have sort of this patterning. We need to have a minus R, a 1 plus 2R, and then another minus R. So we can start off by creating 3 separate arrays of just that fill. So size n, and the value is minus r. And then we'll have another that is again that size, and now we're gonna have 1 plus 2 times r, and then again just another one of these, so I'll just copy paste it over. Cool. So now we have these 3 separate arrays that correspond with each of these, and we basically just want to create this into a list. So we'll then go back here and we'll use np stack to create this into a singular list. And we're going to store this into matrix named AB. Beautiful. Now we need to define what matrix B is. And matrix B really is this here. And I'm actually going to change this up a little bit just for sake of continuing order properly. So we see if we're starting from the left to the right, we want our right to be at the very end. So I'll change this to where we have our t at the 97th position at time n. So r times that plus 2r dr. Right? So when we create this matrix, we're basically following this general form. So let's do that. So we're gonna have to create each one of these independently, because we want the temperature to the left, the temperature in question, and the temperature to the right. And I believe the best way to do that would be, so we want first everything to the left. So we want to exclude the values at the very right. So we're going to do basically in our T array, everything from the left going on to the right of that array. So that'll look like this. Basically, we're just excluding that last 80 value, right? And this, so we'll multiply this by r. So r times that. And then plus, what's our middle? It's 1 minus 2r times everything in the middle. So we're going to go 1 minus 2 times r times our t from 1 to minus 1 should give us that. And then we lastly will have, this should be a plus over here. I don't know why that's not letting me do that. There we go, that's a plus. We have everything excluding our very left value. So we're gonna kind of mirror what's going on over here. Times t. We're gonna start at 2 now and go everything until the very end. Okay, and it seems to be working out. So now I'm gonna shove this into another value, b. It's taken a minute, but while I do that, we recognize that we actually have to adjust these last couple terms to fit our initial and our final states. And the way we can do that is we will go, so B position 0, and we'll hit it with the plus minus operator, is going to be our r times t0. And that will now adjust it by what we need it to be adjusted to. So using this value here. And we'll do the same for our rightmost value. Exactly like that. So we've constructed our AB array here, and then a B array over here, and now what's left is to solve for our unknown arrays here. So that's what we'll be doing next. So our SciPy library will actually give us a solver for banded matrices like this. So we'll do SciPy lineage that's solve banded. And this will actually give us this matrix here, our Tn+1 unknowns. So let's give it its inputs. The first input is how many upper and lower bounds we have. We have one upper bound, that's our TL. We have one lower bound, that's our TR. We give it the matrix AB, that's why I named it as such. This is giving it our stacked matrix. And then B, which is our product matrix, that solution right hand side. And now if you shift enter, it says it's not compatible. Okay, so basically what Python is telling us is that we have a shape disagreement between A, B, and B. And that we can actually show if we look at the shape of AB and the shape of B. We see that there is a mismatch. These two middle values actually need to agree with each other. And the way we can do that is we'll go back up to our AB array and we'll hit -2 for each of these sizes. And now these agree and it gives us an output. So this is actually the temperature profile now for our time T+1, or N+1 rather. So we see that we have some propagation of our temperatures, and then we reach this middle where it's mainly untouched, and then we start increasing again as we reach our final face, our right side face. So now we understand that since we were able to do this for one time integer, we should be able to do this now for all the time integers. So we'll have to construct a for loop that'll give us each of these temperature profiles, and then same way we can be able to plot it out beautifully just like this. So what's nice is that we can kind of use this, what we have over here, as kind of a guide to help us do this. So what we realize now is that, let's just store this into some random thing, right? Y. If you look at the shape of Y, it's 98, and we want to update the size of our temperature. But if we see the shape of our temperatures, it's 100. So actually what ends up happening is we don't want to update the entire T array. In fact, we only want to update what's between 1 and -1. Because this is what gives us everything in between our left bound and our right bound. So up here, I'm going to create another T profiles, and that's just going to be a copy. And we don't need to keep redefining this, so I'm actually also going to throw this up here. So this will be our AB. And now I'm going to throw in a for loop. So for I in range, I don't know, let's say 100 for now. We basically want to keep doing these B calculations iteratively, and then doing this calculation at the very end. And then we want to append, so tprofile.append a copy of our new T array, because it keeps getting updated as we keep doing our our loop. So that should be good. This should be giving us now. Let's see what our final is. So let's see what -1. Okay, maybe not exactly at our final steady state just yet. There's a bit of a dip and then we go back up. So maybe that just means we need to run it for a bit more time. But what I'm going to do is I'm actually just going to copy and paste this over here, down here, so we can actually maybe take a look. Yeah, let's run this longer. Let's see what happens. There we go. So it actually looks like we do reach somewhat of a steady state. Let's see more of these. Yeah. See, now we actually see that there is a progression and an evolution of our temperature profiles as our temperature propagates through our bar over time. And we actually reach this final steady state because we reach a final steady state evidenced by this straight line that connects from our initial to our final temperatures across our bar. So this actually does give us at R equals 2, where remember our R actually failed when it was greater than 0.5 for our other temperature profile. But we see now that our R, even though it's a much higher value, 4 times the value of what we have set as our limit for this analysis method, we actually do get a stable solution for our temperature profile. So that's pretty neat. So let's actually try and push the limits of our R value here. Let's see how high it can go. We already are at 2, so we've already exceeded the limit of our traditional solving method, but let's just see. So now we see that we actually do still get a very solid solution, but we're kind of taking bigger jumps between each. So like maybe bigger time steps in between each of these lines. So let's just keep going. Maybe we can push it to 100. Okay, so our values aren't going off into infinity, but now we see that we have some obstructions here towards the beginning and the end. And they become a bit more prominent as we keep pushing the limits of our R. So let me maybe zoom in here and see what's actually going on. So the reason that we have these little ups and downs, these little dips, isn't because of the stability of our solution. In fact, it's now a figure of the accuracy of our solution. So if you remember before, we defined this R value here. I'll write it off to the side here somewhere. So we had stated that we have an R value that's equal to alpha delta t times 2 delta x squared. Well, let's say if I wanted to analyze this for maybe even smaller widths of x. So maybe instead of 1/10, maybe I want to go 100th of a meter. Well, we realize that this diminution of our width actually increases in magnitude because it's squared. So this actually turns into a factor of going down by 1/10,000th of a meter, for which this time step then becomes much larger to account for this R value. So that's actually what's happening when we increase the R value in our code here. We are losing accuracy because we are essentially estimating a derivative. We discretize that derivative into a spatial differencing. And so now, because we are using this spatial derivative method, if our position or if our R value changes and becomes much larger, our time jumps become much larger, we're losing accuracy in that derivative for which we are estimating. So that actually becomes the reason for why we have these obstructions. These are actually just inaccuracies in the estimation of our derivative. So going back down to something more reasonable, maybe say 1, we still do get these nice bands. And what we've essentially created is a method that is less susceptible to sensitivity due to our R factor, but becomes a little bit more susceptible to the the inaccuracies of the estimation of our derivative according to our time jumps.